All right, we're going to go ahead and go into the types of waves. So the first type of wave that we're going to talk about is called a transverse wave. And transverse waves are also called shear waves, and they're disturbance in the perpendicular direction to the direction of propagation. So the waves here in this case are propagating this direction, and the disturbance is in the perpendicular direction, okay? So this is the disturbance. Direction, okay? And this is the direction of propagation, okay? So this is called a transverse wave, and some examples of this type of wave are like in the strings of musical instruments, electromagnetic waves, just like visible light. Okay, then we have another type that's called longitudinal waves. They're also called compressional waves, and this disturbance is parallel to the direction of propagation. So not only is the direction of propagation in this direction, so is the disturbance. So the disturbance and the propagation are in the same direction, okay? And examples of this are sound waves in air and in water, in basically any type of fluid, okay? Now, an example of kind of like a combination of the two, things that have both of them, or have transverse and longitudinal components of them, are water waves, sounds in solids, and earthquake waves, such as P and S waves, okay? If you've ever taken a geology course or environmental science course, you may have talked about earthquake waves, but if not, that's okay. Just to get the idea that there are both types of waves in these different real-life situations, okay? So what happens if we have both of these, or multiple waves trying to interact, okay? That's where we get this term called superposition. So we get a superposition of waves, and that is a disturbance on waves that are superimposed when they come together, okay? So superimposing them just kind of means that they're coming together, okay? And we can get two types of interferences when this happens, okay? This is going to be called constructive or destructive interference, okay? So when we have constructive interference, this is when two waves come together and they are identical waves. They arrive at the same point in phase and result in the addition of the two. So that's what we have here. Okay, so this is going to be constructive interference. Okay, so we have two waves that are in phase with each other. So see, they get hit peaks at the same time and the low points at the same time. Okay, so they're in phase with each other, and so when they come together, they add together. So this is their resultant, is what it's called. Okay, the resulting wave. Then we have destructive interference. That's this one up here. Okay, so this is when we have identical waves, but they're exactly out of phase. Okay, so when the first wave hits a high point, the other one hits the low point. When this first one hits the low point, the other one hits the high point. Okay, so this is called destructive interference. Okay, so the resultant of these two waves is 0. Okay, so it's just a flat line. So when these two waves come together, this is exactly what happens. Okay. All right, then we have another idea, which is called standing waves. And these waves move through each other with their disturbances adding as they go by. Okay, Again, let me restate that. The waves move through each other with their disturbances adding as they go by. Okay? If the two waves have the same amplitude and wavelength, then they alternate between constructive and deconstructive interference, and the resultant looks like a wave standing in place. Okay? So here are some ideas. Okay? First one we have is they're just adding together. Okay? Similar to the last one, but they are going in the opposite direction. But they still add together. Okay? Then we have, let's go to the exact, no, this one here. Okay? So now they are, let's see. No, I want to go to I'm sorry. So the second one here, they are exactly out of phase, it looks like. Okay, so the resultant is 0 again, and so forth. So we're getting the same idea here. Okay. This is going to be, one of the main things I wanted you to get out of that was that first statement I made, is that the waves move through each other. Okay. All right. A little bit more on standing waves. They are found in musical instruments and are due to reflections of waves from ends of the string. Okay, and there are 3 types here. Okay. Okay, so in order to look at these different types, we need to make a few definitions. The first thing is we need to understand what a node is, and these nodes are points where the string does not move and the wave disturbance is 0. Okay, so the nodes are going to be these points here, 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 all of these points where the wave disturbance is 0. Okay, then we have the antinode. The antinode is the location of maximum amplitude in the standing wave. So the antinode in this first one is going to be the peak here, and then here it's going to be same here. Okay, and then we have a fundamental frequency, which is the lowest frequency and the longest wavelength. So wherever the lowest frequency is and the longest wavelength. Okay, so these are the fundamental frequencies. And then we have overtones or harmonics, which are the multiples of the fundamental frequencies. Okay, so we have the fundamental frequency here, first overtone, and then second overtone. Okay, so just understand the idea of this and how to kind of look at these figures and understand, I would say, how to label this, what all of these things are. Okay, remember that your wavelength, or what your wavelength is, and so forth. Okay, so these are about standing waves. Now let's move on to the energy in waves. We're going to look at it a little differently and talk about intensity. So the intensity of a wave is going to be equal to the power carried by the wave divided by the area that it travels through. Okay, so this is the intensity of a wave. And in SI units, this is going to be in watts per meter squared. Okay, remember that power is in watts and area is meters squared. Okay, and I show you this. This is an earthquake that has taken place, kind of the aftermath, right? The aftermath of an earthquake. And this shows you the types of intensity for waves that can happen. So this is an example of intensity in waves, right? And this intensity in earthquakes are measured by what we call the Richter scale. Okay, so the intensity or the power over the area is measured by the Richter scale. Okay, so this is, again, a real-life application. Okay, so I'm going to start with this example 16.9. The average intensity of sunlight on Earth's surface is about 700 watts per meter squared. Okay, that's my intensity. And in part A, it asks me to calculate the amount of energy that falls on a solar collector having an area of 0.5 meters squared in 4 hours. Okay, so what is my energy? Okay, so my intensity is, remember, power over area. Okay, what is power? Take a second, maybe to look back and remind yourself what power is. Okay, so hopefully you were able to look that up or try to remember. Okay, our power is equal to an energy over some time, some energy per unit time. Okay, so this is here. So we want to find that energy. Okay, so energy now, if I use this equation, equals to my intensity, that's going to be energy equals my I times A times T. Okay, this is my energy times my intensity times area times time. So my energy then, if I plug in all of my numbers here, we have 0.5 meters squared, 4 hours. We're going to have to convert that to seconds. There's 3,600 seconds in an hour. Okay, so go ahead and use your calculator. 700 times 0.5 times 4 times 3,600. So again, we are calculating the energy that falls on a solar collector. Okay, so this is the amount of energy. It's 5.04 times 10 to the 6th joules. So that is my energy that goes onto my solar panel, you could say. Okay, now part B, what intensity would such sunlight have if concentrated by a magnifying glass area onto an area 200 times smaller than its own? So what would the intensity be if it was 200 times smaller? Okay, so we have I, okay, equals my E over T over A. And we're saying the area is 200 times smaller. So what I would say be T times 1 divided by 200 times A. So I can plug everything in. Okay, so my energy I just solved for, 5.04 times 10 to the 6 joules, over my time, which is 4 hours, times 3,600 seconds over hours, and then times 1 over 200 times 0.5 meters squared. So again, it's 200 times smaller than that original area. Okay, so I plug that into my calculator and I get 1.4 times 10 to the 5th, and this is in watts per meters squared. So this is my new intensity. I can call it I prime. Okay,